everybody. My name is Omer. I worked as a security researcher at Deep Instinct. And today in my lecture, I'm going to talk about WMI and DCOM lateral movement prevention. First, I had to say that this research originally made by Eliran Nissan, a team member of mine. He can't be here today, so I present this research today. So this is our agenda for today. We start by present basic concepts on the COM and DCOM protocols. We continue and present some countermeasures that exist today that can handle lateral movements attacked, but then we explain why are they not good enough to prevent DCOM and WMI lateral movements. Later, we present our COM object research that finally led us to build the DCOM-WMI firewall that can handle these attacks. So let's start with a very basic definition of the following protocols. We start with the COM protocol. The COM protocol is a Microsoft standard that enable a binary component to interact with each other. And the DCOM is an extension of the COM protocol that allow this object to interact with each other over the network. The WMI is a remote Windows management protocol, and it's based on the DCOM protocol. And since WMI relies on DCOM, we focus our research on the DCOM protocol in order to prevent them both. We talk about WMI more in depth later in the presentation. So as I said, this was a very basic definition about the COM protocol. So let's drill down into the COM standard. So a COM object can be described as an instance of compiled code that provides a service to the rest of the system. That code defined as a COM class. COM class implement the functionality a COM object can provide. And each COM class has a specific ID called the CLS ID. That CLS ID associates the COM class with its implemented file on the system. And this file can be a DLL or a execution file. COM interface can be described as an abstract class. It defines a set of methods that provide some service. COM interface provides a set of methods that the implemented class must provide. All the communication among COM objects is based on these interfaces, and interfaces can inherit from each other. Lastly, we have the method, and this is a functionality that an interface provides, like write file or run file. One important interface is INOWN interface. All COM interface inherit from this interface. And one important method of this interface is the query interface method, which returns a pointer to a requested COM interface if the COM object supports it. Okay, so COM interface implement in CPP as a pointer to a vtable. A vtable is a struct that built like an array, and each entry of it holds a specific pointer to a specific method the interface provides. The communication between COM objects are based like client and servers. The client is the calling process that requests to create a COM object, and the server is the implemented file on the system, which again can be DLL or execution file that can implement and create the requested object. There are three server types. The first one is in-process server type. In this case, the implemented server is a DLL that loads into the calling application using the COM library. Our second case is local server, and in that case, the implemented server is an independent SPE file that hosts the implemented class. Our last server type is a remote server, and this case is similar to the local server, but at this time, the implemented PE is located on a remote server. In all server types, the client will communicate with its server using its own in-process COM object instance. Okay, and in case of a local or remote server type, this object acts as a proxy object that forward calls to the server using RPC and return the result back to the client. From the client point of view, it does not matter if it's a part of a in-process or a local server type that represent a COM session, or if it's a part of a remote server that represent a DCOM session. So this second part of the introduction presents a countermeasure that exists today that can handle lateral movements attempt. The first method is port and protocol network filtering. This approach, according to this approach, we should block any network traffic that associates with lateral movement attempt. This approach involves blocks specifically protocols that are commonly used in such attacks. For example, we can block the ports 445 or 135, which are mainly used by SMB and RPC. However, this is all or nothing approach, and this could be very difficult to implement in a managed domain since many Windows processes and tasks are relied on the same protocols. The second method we'll talk about is process level monitoring. And according to this method, we should look for leftovers created by some lateral movement attacks. Let's give an example for each one of the following protocol for a leftover we can look for. For a RPC protocol, we take the example of create a remote service. When a remote service is created, we can look for a new binary that runs under services exe, as well as a new registry key created that describes the new service. We can also look for event in the event log that alerts a new service creation. For DCOM-based attacks, many of DCOM-based attacks will cause the remote process DCOM launch exe to spawn a new child process. This process can be CMD, PowerShell, or any malware designed by the attackers. And we can also look for a new event log that describes basic details about the DCOM session. When WMI queries interact with a remote computer, it will cause WMI provider to load into the remote process WMI PRSVE. And we can monitor these queries as well using ETW, but at a cost of detect them and not prevent them. So as you probably understand, this approach relies on indirect evidence that could cause a lot of false positives. And second, not every lateral movement attack leaves any of these leftovers. So the next two methods we'll talk about handle lateral movements attacks that are using the RPC protocol. The first one is RPC filtering. RPC filtering is served like a host firewall, and it's allowed to block a specific RPC interface, and while still allow other RPC interface to function. This allows more flexibility when block RPC traffic. For example, by block this specifically IID that associates with service interaction, we can completely block interaction between services among the network while still allow other RPC interface to interact properly. One big disadvantage of this method, is that we can only block the entire interface and not a specific action. means we cannot block only remote service creation while still allowing other service interaction. There is also the possibility to capture RPC calls using ETW. There is some events that can expose both the IID and the specific method that's used in an RPC call, but in a cost of detect it and not prevent it like RPC filtering does. So after we got familiar with the RPC countermeasure, we learned that RPC defense works well against RPC attacks, and because of that reason, many attackers are already leverage DCOM and WMI lateral movements. One more reason to this shift is that both DCOM and WMI are well documented among the security community, and there is a lot of attack tools that developed based on these protocols, such as CobbleStrike, PowerSploit, and many more. Second, both of these vectors enable by default on Windows environment and consider a legitimate traffic inside the managed domain. So it means that attacks that based on this protocol can blend easily with the legitimate network traffic, and this will make it harder to detect. Also, there are many threat actors that utilize DCOM and WMI, and one example is the Muddy Water, an Iranian attack group that developed a malware that spread to other entries using DCOM. So after we got familiar with DCOM and we learned about some defense against lateral movement attacks, we can start explore method to prevent DCOM and based lateral movements attempt. So our first attempt starts by place a hook inside the vtable on a specific method we would like to monitor. So when this method call, execution pass to us. But the only problem is that not always we will have an instance of the COM object we want to monitor. That means we should hook COM object creation as well. The two commonly used API to create COM object are co-create instance and co-create instance X. Both these API receive CLS-ID and IID as a parameter, which represent the specific object to be created. By hooking these APIs, we can check these specific parameters, and if they match one of the objects we would like to, which contain one of the methods we would like to monitor, we then redirect the method pointer inside the vtable to a pointer of our hook monitoring logic. So this is the hook we place inside co-create instance and co-create instance X, and every time it will be a call to one of these functions. First, we start by creating the requested object and save the result. Then we continue to check the CLS-ID and IID's parameter against the CLS-ID sample object and IID sample service, which represent the specific COM object we are looking for. And if they both match, we proceed to hook the desired function. In this example, we want to hook the query interface method and the do-work method. And as you can see, it's done using the function hook vtable method. So this is the hook vtable method, and its implementation is quite simple. First, we check if the method we want to hook is already hooked by comparing the method address inside the vtable with our hook function address. And if they match, it means the hook is already in place. And if not, we simply place the hook by replace the original method pointer with a pointer to our hook method. So after we implement this hook, we can write a simple PowerShell script that implements DCOM lateral movement attempt and confirm this hook technique can block DCOM lateral movement attempt properly. This is the PowerShell script I'm going to use. It's utilize the shell execute method from the COM class shell windows, and it uses it in order to run the calc application on a remote IP. So before I ran this PowerShell script, I opened WinDBG and put a breakpoint and attach it to the PowerShell process first. Then I put a breakpoint on core create instance and core create instance X, which is the function we just hooked. But surprisingly, neither of the breakpoint was hit, which indicated that neither of the function was called during the file execution. So let's add this, our first attempt to our research flow. So we try to put a hook on COM object creation like core create instance and core create instance X, and we fail to block our PowerShell test. We then understand we need to further deeper about COM object creation and discover new findings. First, Windows API provides many more functions to create COM object beside co-create instance and co-create instance X. Here you can see some example, and this is only the small part of the available options. Second, not every COM object are created by a direct API. There are some objects that are hidden inside other objects. As an example, we can take a look of our PowerShell POC, and we can see that the shell execute is hidden inside the OBJ field. So what should we do? Hooking every API can be very complex, messy, and easy to bypass. So as a solution, we changed our focus and decided to hook based on the DCOM runtime behavior instead of COM creation. And I'll explain how we did it on the next section. So most of the DCOM lateral movement attempts that are available for the public are implemented using PowerShell or .NET. And this is also the case with our PowerShell script. I want to convert the PowerShell script into CPP. And the reason we need to do this conversion is because our goal is to investigate the last application object in memory, because it provides the shell execute method we would like to block. And the second step is to investigate the code that shell execute points to. And this will best achieved using C or CPP. So we need to convert all the properties appear on the PowerShell script into CLSID, IIDs, and C method. We already have the CLSID on the PowerShell script, but we are missing the IDs that OBJ represent. We can discover we can discover the IIDs of our PowerShell that appears in our PowerShell script using the get member command minus input object. This command receive object as a parameter and return more information. And one of the information is the IIDs we are looking for. So I start running this command on the OBJ and got back its IIDs. Then I keep running the same command to the rest of the object that present on the PowerShell script. And finally, we learn that our application object we're looking for associate with these following IIDs that point to iShell dispatch 6. So even though shell execute is called from iShell dispatch 6, it was originally defined on iShell dispatch 2, and all later interfaces like iShell dispatch 6 inherit it. So the next hook I place it inside iShell dispatch 2 and not iShell dispatch 6. So after revealing all these IIDs of the properties appears on the PowerShell script, We can now look them up on MSDN and OLE view and use this new information like the interface name, definition, and C header files, and in order to build our CPP shell Windows client, which is basically a CPP implementation of the PowerShell script. So the full implementation is a bit longer than the PowerShell script, but here you can see the main point. And the main point is we can get a handle to iShell dispatch to, and we want to use it in order to find a pointer to shell execute and look at the code it points to. So after we got the pointer to iShell dispatch to, we can't use the following syntax on CPP in order to return an address of a class method. So instead, I'll use the following C interface preprocessor definition. It will change treatment to all the DCOM objects from CPP classes into C structs that represent their respective vtable. On this object, we can use the offset of function, and we declare a new function called getOffsetShell dispatch to shell execute. And we use offset of to calculate the offset of shell execute method inside iShell dispatch 2. We use our new method we just declared in the following code, and then we can calculate the index and the address of shell execute. So let me make it clear. We can calculate the specific index inside the vtable of shell execute, and we can return shell execute memory address as well. So after we run the script, we'll learn that shell execute is placed on the 31 index inside iShell dispatch to vtable, and you can see its memory address as well. Using this address, I opened WinDBG and disassemble the address content. And then I can see immediately shell execute point to the internal symbol object tabless client 31. As you can see in the picture, it starts by set EAX to 1F and then transfer execution to object tabless client. If you don't know, 1F in decimal equals to 31, which is the exact index we discover inside the vtable that shell execute placed on. So with that new information, we open COM-based DLL and look at its symbols and export. We then can see immediately that there is a lot of function from the formation object tabless client and the number between 3 to 2047. Each of these functions start by set EAX to the number specified in the function title and then transfer execution to object tabless client. Here you can see object tabless client implementation, and object tabless client in turn transfer execution, object tabless in turn transfer execution to object tabless client. So let's do a mini summary until now. As we remember, every COM object that is part of a DCOM session implemented as a proxy object. And we just discovered that every DCOM method invocation, including the ones that allow lateral movements attacks, finally execute object tabless and object tabless client. So which functions should we hook? By looking at object tabless signature, we can learn that it does not have a fixed signature and its parameter can be varied depends on the situation. Object tabless the object tabless can support many variable because it creates a pointer to its own stack and send it as a parameter to object tabless. Since the rest of the parameters are already aligned in the stack, object tabless client use this pointer as a reference to the rest of the parameter. So we learned that object tablets handle its parameter and stack in a special way, and hookit can disturb the parameter passage and the stack formation and may cause it to crash. Object tablets client on the other end has this straightforward and stable signature, and we choose this function to place a hook on. When placing the hook, we will check the method parameter, and this parameter specify the specific index inside the vtable of the object that we want to call. So, in order to place a hook inside object tablets client, we need to know its function address in memory. But the problem is object tablets client is not an exported symbol. However, we can still get its address using the fact that object tablets client 3 is an exported method. We start by byte parsing object tablets 3, and as you remember, we say that all of this function has a specific formation. They all start by move ex value and finally transfer execution to object tablets. So we can extract object tablets address from this jump instruction. And once we have object tablets address, we can parse it, and as a reminder, here is the object tablets function, and it ends with a call to object tablets client. So again, we can parse this call instruction and get back the object tablets client address. Here you can see the hook we placed inside object tablets client. This hook logic is to check, to look for a specific IIDs and a specific method. And in this hook, you can see we check whether the IID is iShellDispatch2 and the method is shell execute. We check the method using the method parameter, and if it equals to 31 that indicates the shell execute method, we know we found what we are looking for. So now that we place a new hook, we can try again to block our DCOM lateral movement attempt. Our PowerShell script try to commit. So after placing the new hook, we run again our PowerShell script, but unfortunately also this time we failed to detect the attack. The next part explains why and present an improved solution. So again, let's add our second attempt. We try to put a hook on object tablets client, but it won't work, and we fail to detect the DCOM lateral movement attempt. So to understand why, I opened WinDBG, and I figured out that our PowerShell script does not trigger object tablets client at all. In order to understand why, I searched the answer on the network traffic. I start by capture the communication created by our CPP implementation, and I saw a clear interaction with iShellDispatch2. Then I compare the network traffic that generated by the PowerShell script, and I can no longer see interaction with iShellDispatch2, but instead I see interaction with iDispatch. So what is the difference? iDispatch is a key interface that enables script languages to interact with each other. Many interfaces implement iDispatch, so they can be used from different languages. iShellDispatch2 also supports iDispatch and invoke its shell execute method with iDispatch invoke. iDispatch invoke is used to call a specific method on a COM object. So now that we understand that PowerShell runtime use iDispatch invoke in order to invoke shell execute, we can look for the internal method of iDispatch invoke, just like we did with object stateless client. So the process is completely identical. We first implement a use of iDispatch invoke, and then we use the pointer to iDispatch in order to calculate the method index inside the vtable and the invoke method memory address. And after we got invoke memory address, we can use again WinDBG, and then we learn that iDispatch invoke point to the internal API called iDispatch invoke proxy. As you can understand from the name, every COM object that implements iDispatch will use this function for iDispatch invoke capability. This makes iDispatch invoke proxy our hooking spot for DCOM lateral movements that are using iDispatch. When place this hook, we will check the DIS-PID member, which specifies the name of the method that's being called. So this is the hook we placed inside iDispatch invoke proxy. The logic is completely the same. Again, we're looking for a specific IID and a specific method. So now that we place a hook on iDispatch invoke proxy and the object stateless client, we can give another try to block the PowerShell script that performed the DCOM-WMI lateral movement attempt. And this time, we finally successfully blocked the attack. So let's put our third attempt into our research flow. We put a hook inside object stateless client and inside iDispatch invoke proxy, and we finally successfully blocking the DCOM lateral movements attempt. So until now, we talk only about the COM aspect and the proxy aspect of a DCOM lateral movement attack. And in order to make our code more effectively, we can filter out COM objects that are not part of a DCOM session. So in order to do so, we need to know two things. First, I want to confirm that the specific object I'm looking at is a part of a DCOM session. And if it is, I want to identify its IP address of the server it's connected to. We can answer both of these questions using the help of IRPC option interface. This interface provides information about the RPC session of a COM object. The function we will use from this interface is the query method. It can query for two properties. The first one is COM-BND RPC timeout, and the second one is COM-BND server locality. We will use the second one, and this property can hold three different values. Specifically, we're looking for the server locality remote, which indicate that the COM object is a part of a DCOM session. So using this logic, we can create the function isCOM-object, and it simply check the server locality property and return true if it equals to server locality remote, which means that the current COM object we're checking is a part of a DCOM session. For identify the server IP, this is more challenging than expected, as the COM protocol does not provide this information at all. Technically, if we had the RPC binding handle, we can use these two following APIs in order to get back the remote server IP address. First, we will need to make use of our first API, RPC binding to string binding. This API creates a string representation of an RPC handle. And the second API, RPC string binding parse the IP address from a string representation RPC handle. We can get access to the RPC binding handle using, again, the query method from the IRPC option interface. we need to create a call to a RPC query to the property combine the RPC timeout. Under the hood, this call, this task accomplished by making use of the following API called RPC MGMT INQ-COM timeout. And as you can see, one of its parameters is the RPC binding handle, and this is exactly what we are looking for. So we hook this method as well, and this is how we get the RPC binding handle. So until now, we only talk about DCOM-WMI, DCOM lateral movement prevention, and this part explains why the method we talked about along the presentation are also prevent WMI-based attacks. First, we will talk about the WMI architecture. We start with the WMI providers. WMI providers are a COM object that manage a system component. These components can be logical, like services and processes, or they can be physical, like a hard drive and network card. The WMI infrastructure relies on WMI service, and its role is to manage the communication between a WMI provider and WMI consumer. A WMI consumer is a client script or application that interact with the WMI servers in order to perform action or access system information. The action WMI consumer can do depend on the specific providers it communicates with. So the communication between WMI is based also using COM interfaces. And if it sounds familiar to you, this is because this COM interface acts as a COM proxy object that manages the communication between the WMI client and the WMI servers on a local or a remote server. So let's walk through a high-level flow of remote WMI operation. First, we start by initial the COM library using a co-initial X. Then we obtain a pointer to IWM locator, which is the initial entry point to WMI, and it's achieved using the co-create instance API. Once we have a pointer to the locator, we can use it to call to the connect server method, which connects us to the remote system. This will obtain us a pointer to the IWM services, and we can use this pointer as this finally will be our client interface, and we can use it in order to perform various of WMI queries. Here you can see some example of the query type we can perform. Exec notification query allows us to register to system events. Exec query enable us to access system information, and exec method allow us to execute a remote providers method on remote computers. So all of the WMI, most of the WMI lateral movements attacked based on execute a remote providers method. Such providers can be Win32 process and the method create in order to run a remote process on a remote machine, or the Win32 product and the method install that can install a remote MSI on a specific computer. As executing a provider method is done with the IWM service and exec method, we can simply place a hook on this method and look for a specific providers and method we would like to monitor. So now I'll present a demo of our DCOM-WMI tools. In the demo, you can see a use of this following executable. This is a file that contains various of DCOM-based and WMI-based attacks. So I will execute one attack for a DCOM lateral movement attempt and the second attack for WMI lateral movement attempt. So let's see how it looks like. This is the first attack for the DCOM. It uses shell execute in order to open calc on the remote machine. You can see that there is a log file that creates down below. And this is the second attack. It uses a WMI to run a calc. Here you can see the log event that creates for the DCOM attack. You can see we identified the use of shell execute. And you can see there is another log for the WMI attack. You can see that we identified the use of a Win32 process PROIDEA. And you can also see the command line as well. Okay, so this was the demo. And thank you. Thank you. So let's summarize all the things we talked about. We start by present the COM basic component and continue by discussed about some of the countermeasures that exist today and explain why are they not good enough for blocking WMI and DCOM-based lateral movements attacks. Then we present our research process that finally lead us to place a hook on object stub client and iDispatch invokes proxy APIs. Then we improved our logic and was able to identify also the remote IP that the COM session communicated to. And lastly, we show the demo of our DCOM WMI firewall. Questions?